Next, we are on page 279, and I didn't skip anything here. I'm just following the notes right now. And so this is the activity 25. The focus is center of mass. And we are going to look into a case where we have like two collision carts. And one of them has a plunger. I will show a picture of that. Let me do that first. So this is the plunger, and you can push that in, and then the top little pin is gonna come up in that case, and then there's a spring load, and so you can push it in, so kind of compress the spring, and again that gives the elastic potential energy, right? And then you can use that to if there's another cart coming towards it, you can use that energy, and then you can release it when they hit each other, and then that will give it a kinetic energy. Okay, so you can even think about energy conservation. So I'm gonna show a video later, but let's just kind of understand the theory behind this. So first of all, we will consider a track that is balanced. Okay, so there's a fulcrum. In the video, I'm gonna use a wooden block. So the track will be balanced on the wooden block. Okay, and two carts are placed on the track with their combined center of mass directly above the fulcrum point, so that the track still stays in balance. And to maintain the we are using that for to maintain the balance. And one of the carts has a spring-loaded plunger, as I showed in the figure, and that can be triggered. So if we push that pin, then it will release the spring, and then again the elastic potential energy will turn into kinetic energy. Okay, assuming there no friction, no air drag, anything like that, and it's leveled, so there's no change in elevation, or there's no heat temperature changes or anything like that. Okay, so the once we trigger that, and it will cause the two cars to be propelled away from each other, so they picked up some speed. Okay, in the space below, we want to draw our free body diagram for this two cart system. So we're now looking at one or two separately. We are looking at the system. For the system, the plunger, yes, there's a push between them, but it becomes an internal force, right? Because you're looking at the two cart system. Although there's force between them, again, that becomes internal, so you don't show that on the free body diagram. We have the weight force, that's the total, downward at the center of mass point. Since the cards are also like the same cards, we expect the center of mass to be right at the in between them, right? So that's the center of mass point, shown as a red dot on the free body diagram. And there's also normal force on the wheels from the track, but instead of showing like 8 different normal force, we just show one vector pushing it kind of up. So along this direction, we can kind of think this in terms of x and y, like that. So the motion happens along the x direction, but along the y direction, those are the only forces we have. We don't really have any other force along x direction. The y components will balance out. That's why the system is not accelerating up or down, right? As we've been doing before. But along the x direction, we have no forces. So that would mean that it shouldn't accelerate. The center of mass point should not accelerate along the x direction either. So if you write that equation first, I don't know how I've done that. So this is our general equation. Sum of fx equals to total mass of the system, so it will be m1 plus m2, and the center of mass acceleration along the x direction. Okay, so you write that and then think about what is the forces. Look at your free body diagram, you have nothing. That goes to 0. That will mean, since there's mass, but there's no acceleration then, right? No force, no acceleration. And if the acceleration is 0 along x direction for the center of mass point, what does that mean for the center of mass point of the velocity for the x direction? It should be constant, right? Because acceleration is 0. What is acceleration again? It's the change of velocity over time. No acceleration means there's no change in velocity. Velocity along the x direction should stay constant only for the center of mass point. And we will see that the pieces are moving, but center of mass point is not gonna move because initially that velocity was 0. Finally, it should stay 0. Throughout the motion, it should stay 0. Okay? But again, that's only for the center of mass. It doesn't mean that the objects are not going to move. Pieces will be moving, center of mass point won't be moving. That's what it means here. So, yeah, center of mass of the system never moves. So let's look at the video now. So here's the case, slow motion. So he's touching the plunger. Again, you can see the plunger pushing them. Look at the track. It is still leveled. Okay, the pieces are moving, but because the center of mass is not moving, it's not changing the or messing up the level of the track. But later on, once the carts are coming back from the end, so things are changing because they're interacting with other things, maybe the some other things on the ends of the track and such. So there are some external forces, and then things are going to be changed. But initially, until they interact with anything else, we expect the center of mass not to move because of the second law. Okay. And after this, there are some clicker questions, and you are going to answer them. I will also embed some video clips in them so that you can also check on your understanding.